Welcome to directed graphical models, also sometimes known as Bayesian networks. And let me put Bayesian in quotes here, because there's nothing particularly Bayesian about directed graphical models. They're not really, they're not being fully Bayesian or even partly Bayesian in any sense, because you're not necessarily, when you're using a directed graphical model, there's nothing about that that says that you're putting a prior on parameters or anything like that. So you can have a Bayesian, you could take a Bayesian approach with a directed graphical model, but that's not, it's not essential to what graphical models are. And also, the name, calling them Bayesian is somewhat of an uninformative name. And also, calling them directed graphical models is somewhat of a misnomer as well, because they're not really models. A better name might be, I would say that a better name might be conditional independence diagrams. Maybe not as catchy as the others, but it tells you more about what's going on, because what they are is directed graphs that tell you something about the conditional independence properties of a probability distribution. That's what a directed graphical model is. And they do so by saying that the joint distribution has to factor in a certain way. So the key notion behind graphical models is factorization. That is the essential thing that's going on in graphical models, factorization of the probability distribution. So why are they called graphical models? Where's the graph part come from? Well, they're a notational device. The graph part is a notational device that's extraordinarily useful for visualization of two things. Two, sort of closely related things. The first one is, as I said, the conditional independence properties. So it's visualizing the conditional independence properties of a probability distribution. And also, and somewhat related to A, is visualizing inference algorithms for a particular model, for a particular probability distribution. And inference algorithms that are often used on graphical models are things like dynamic programming and Markov chain Monte Carlo and so forth. So why do we care so much? I keep on talking about this conditional independence. What is so essential about conditional independence? Why do we care so much about this conditional independence stuff? The reason why, so why is conditional independence important? And the reason is tractable inference. When you have nice conditional independence properties for your distribution, then you can do inference much more efficiently by exploiting those properties than if you didn't exploit them. So that's really what it all sort of comes down to, is being able to efficiently do inference. That's why they're sort of useful. Okay, so I think I've rambled on enough about this. Let's start looking at what they actually are. So before I give you really just the full general thing, I want to motivate it through some sort of natural build up to the sort of general thing. So we're going to look at some simple examples first and build up to it. So let's start thinking graphically. And what I mean by graphically here, of course, I've been talking about graphical models and graphs, and by a graph I mean a graph in the mathematical sense, which is colloquially, if I can say that correctly, called a network. And it's just a network is just something like this. You have some nodes and links, people might say. And in math, we usually refer to these as vertices and edges. So the vertices are the nodes and the edges are the links. And a directed graphical model is one of these where the edges are directed. So each of the edges has, it's an arrow, you might say. So that's what I mean by thinking graphically. Let's start. Can we see if we can associate a graph with a probability distribution? So let's let A, B, and C be random variables, just some arbitrary random variables. And let's think about their joint distribution. So the probability of that A equals little a, B equals little b, and C equals little c, or the density function if you want to think of a density function, same thing all applies. This joint distribution can be factored as the probability of C given A and B times the probability of A and B. And we can factor this again as, so then we have the probability of C given A and B times the probability of, let's do B given A times the probability of A. So we can always do that. Well, I should say, okay, so a neuron should be firing in your head right now saying, wait a second, what if the probability of A and B is 0? Then this conditional probability is not defined. And that is true. That is a good observation if you notice that. But it's not too bad in this case. We can circumvent that difficulty, because if the probability of A and B is 0, even though this isn't defined, this is 0. So if the probability of A and B equals 0, then we interpret this as 0, because the joint distribution, if the probability of A and B, that A equals little a and B equals little b is 0, then this joint probability is 0. So this is a sensible thing to do. And you can do the same thing over here if the probability of A was 0. Okay, that was just an aside, but the main point is we can factor in this way. We can always factor in this way. And what is a graph that we might associate with this? Let's think about if we can associate a graph with this particular factorization. There was nothing special about this one, but let's think about this one. So the natural thing to do might be to take a vertex for each random variable, A, B, and C. And then what kind of edges should we put down? Well, let's see. Maybe for this particular factorization, since C is conditioned on A and B, let's draw some arrows, some edges like that. And here B is conditioned on A, so let's draw an edge like that. And A isn't conditioned on anything. Now, of course, there was nothing. So we got a graph, right? We got a graph associated with this. And if you notice, if you know your graphs, you would know that this is a directed acyclic graph. So it's not only a directed graph, it's acyclic because there are no directed cycles. You can't follow a sequence of edges in the direction of that edge and end up back where you started. So it's acyclic, no directed cycles. So that's kind of interesting, but it's not very interesting because we could have factored this in a completely different way and gotten arrows going in some other directions. But what if, so we were talking about conditional independence before, what if the probability of A, so let's write it this way. Let's just write it. Let's introduce the following notation for conditional independence. Let's say that B is conditionally independent of C given A. Let's use this notation to denote that B is conditionally independent of C given A. So let me say that. Well, okay, we'll just write it. I'll just not do it formally. So let's just use this notation for conditional independence given A. And if we have that, that just means that this thing here factors as the probability, or it's not doesn't factor, but it becomes the probability of C given A. And so if we were to plug that in here and draw edges in a similar way, then what would happen? Let's see. So before we drew an arrow from A to C, and we drew an arrow from B to C, A to C and B to C, but now we would not have the arrow from B to C for this factorization. So we would erase this arrow. And now we're starting to get something interesting, because not every distribution on A, B, and C would have a factorization that would give you a graph like this, right? So we're starting to get somewhere now. Let's start thinking a little more. Let's try to generalize this a little bit more. So we haven't really said anything concrete yet. We're just sort of playing around with, we're just sort of playing around with these distributions and with these graphs. So let's look at another example. Let's say we've got random variables x1 up to x5. And let's look at their joint distribution. So let's go ahead and draw, actually let's go ahead and start drawing the graph while we write down the factorization. We've got some joint distribution, x1 to x5. And let's draw a graph with a variable. Let me just put 1, 2, 3, 4, and 5 without drawing. I mean, I could put x1 to be more consistent. I would put the random variable, but just keep things simple. And we can factor this in a similar way to before. So what are we going to do here? So let's go ahead and do, this is the probability of x1 times, so let me use some different colors here to emphasize things, times the probability of x2 given x1, and now we're going to draw an arrow from 1 to 2 to denote that factor. And then let's switch colors again. Probability of x3 given x2 and x1. And then we get an arrow from 2 to 3 and an arrow from 1 to 3. And then we have another factor here. Probability of x4 given x1, x2, and x3. And we get an arrow from each of these, 1, 2, and 3 to 4. 1, 2, and 3, each going to 4. And we have one more to go. We have, of course, the probability of x5 given x1, x2, x3, and x4. And so we get one more set of arrows. 1, 2, 3, and 4, all going to 5. So we just had some arbitrary joint distribution, and we factored it in a particular way, and we got a graph like this. And now the interesting thing is to start to think about, what if we had certain conditional independence properties here? What if, for example, what if this factored as, or didn't factor as, but what if x3 was conditionally independent of, say, x2 given x1? Then that would be equal to this, and we would drop one of these arrows. We would drop, let's see, we would drop the arrow from x2 to x3. So this arrow would be gone. And you can see that if there were certain other conditional independence properties, like if x4 was conditionally independent of, say, x2 given x1 and 3, then we would drop the arrow from 2 to 4. So this arrow would be gone. And if we applied the similar type of a procedure for all the conditional independence properties, that we could reduce these factors down, then we would get some more sparse graph here with less edges, and not every distribution would be able to factor in such a way. So we're starting to get somewhere interesting now. Okay, I'm out of time in this video. Let's come back and we'll continue thinking along this train of thought.